today's video, we'll start out with a couple of quizkins, and then we're going to move into our last segment on electrochemistry. Today we're going to explore what happens when you're not at the standard conditions. We know how to find E0 cell, that's the cell potential, when you're at 1 atmosphere of pressure, 1 molar for all solutions, 25 degrees C. But we haven't considered differences from that and how to make predictions or account for when you're not at standard conditions. Starting out with this quizkin, we have a current of 2 amps passed through 1 liter of a 2 molar sodium chloride solution, and it goes through for 8 hours. The first question we have to answer is what volume of Cl2 is produced at 25 degrees C and 1 atmosphere? Well, obviously Cl2 is produced. Let's try and figure out why and what the anode and cathode half reactions would be. This is an aqueous solution. So at the cathode, the reduction possibilities would be sodium reduces or water reduces. Remember, our rule says transition metals will reduce preferentially to water, but nothing else. And so, since sodium is not a transition metal, we're going to see water reducing. So our cathode half reaction is going to be 2 electrons plus 2 waters reducing to H2 and producing 2 OH minus. At the anode, well, we have a lower halide. And remember, lower halides will oxidize preferentially to water. And so Cl minus, 2 of them, will oxidize to Cl2 and give up 2 electrons. So that's why Cl2 is produced. Well, let's answer this first question. Well, I've reproduced the cathode and the anode half reactions here, and I've also summed them together to give the overall cell reaction. I can use dimensional analysis to answer this question by just making sure that my units turn out to be moles of Cl2, and then I can use the ideal gas law to find volume. So starting out with my current 2.00 amps, I want to change that into moles of electrons because that's my quickest pathway to find moles of any chemical in this reaction. Well, moles of electrons are related to coulombs, and a coulomb is an amp second. So I think I'm going to multiply this amp, which is a rate unit, by the time. So 8.00 hours was the time. Now I have amp hours, but amp seconds are what coulombs are, so I'm going to change the hours to seconds. 1 hour is the same as 3,600 seconds, so now I've got amp seconds. But 1 amp second is the same thing as 1 coulomb. So now I've got coulombs, and I know that there are 96,500 coulombs in every mole of electrons. That's the charge on a mole of electrons. So I've now converted to moles of electrons. According to my half reaction at the anode, every 2 moles of electrons will produce 1 mole of Cl2. So now I know I'm going to have 0.298, after I do my math, moles of Cl2 produced. So volume is equal to nRT divided by P. So I'll put for N 0.298 moles. R is 0.0821. I'm going to leave the units off, but they're liter atmospheres per mole Kelvin. The temperature was 25 degrees C, so 298 is the Kelvin temperature. And then the pressure was 1 atmosphere. When you work this out, you get 7.30 liters of Cl2 created. The second question here is asking, what is the final pH of this system? Now, to find the final pH of this system, we'd have to identify something that would control pH. And if you recall, in the overall reaction, hydroxide ion was produced, and so that's probably our key. So going back to our reaction, to answer this second question, now I'm going to be working with the first half reaction, the cathode half reaction. So I can start out the same way that I did before and go through all the electrical stuff, but I already know that the stoichiometry of the overall reaction is going to relate Cl2 moles to hydroxide ion moles, and that's going to be my key to understanding pH. So I'm just going to do a quick, simple thing here. Starting out with 0.298 moles of Cl2, I want to convert that into moles of OH minus, and the relationship is, from the stoichiometry, 1 mole of Cl2 corresponds to 2 moles of hydroxide ion. So this ends up being 0.596 moles of hydroxide ion. And this is in 1 liter, it said. So that means my concentration of OH minus is 0.596 moles per liter. So that would mean that my POH is equal to 10 to the negative 0.596, and that comes out to 0.25 for a POH. So pH is going to be 14.00 minus POH, minus 0.25, and that comes out to 13.75. So it's a pretty basic solution after this electrolysis is done. This next quiz can ask us to write the equation for the reaction that occurs, if any, when iron is added to a solution of silver nitrate. Stop the video and see if you can figure this out. I'll give you a hint. Reduction potentials will help you determine if this is spontaneous or not. Well, here's what we're imagining. Here's a beaker, and that beaker contains some silver ions from the silver nitrate solution, and it also contains a piece of iron. So this is the oxidation that could possibly happen if this reaction is going to occur. Fe would oxidize to something. I'm going to pick out 2+. Some say it's going to oxidize to 2+, and that would release 2 electrons. And then here's the possible reduction that could occur. The silver ions that are in here could pick up an electron and reduce to metallic silver. So I need to find what E red and E ox are by looking up reduction potentials from a standard reduction potentials table. Well, here's a pretty good one that I found on the internet. It's got a lot of different values here, and here I have some that are sorted alphabetically. One of them that I'm looking for is right here, silver ion reducing to silver. The reduction potential is 0.799 volts. I'm going to round that off to 0.80 volts. So the reduction for silver, standard reduction potential, positive 0.80 volts. Let's go back and look for iron in that chart. Alphabetically, that should come right here. Now this is an oxidation, so we're going to look at the reverse of the reduction of Fe2 plus to Fe. And that's negative, the reduction is negative 0.44 volts, and so the oxidation would be positive 0.44 volts. So E naught oxidation is positive 0.44 volts. So when we sum this up, we would find our cell potential. E cell is a positive 1.21 volts. Since that's a positive number, that means this reaction is spontaneous, so it will actually occur. Now, to actually answer the question, I'm going to have to multiply the second equation by 2 to make the electrons lost and gained the same. And so my overall reaction is going to be Fe plus 2 Ag plus makes Fe2 plus 2 silvers. Second question is asking us to write the equation for the reaction that occurs, if any one occurs, when manganese dioxide in a hydrochloric acid solution is added to liquid mercury. Stop the video and see if you can answer this question before I give you the answer. If I look at my standard chart of reduction potentials, for something that could happen when manganese dioxide is put in the presence of an acid, which is what we have here, I can find this reaction here where MnO2 is reducing to Mn2+ in an acidic environment. And the reduction potential for that is positive 1.23 volts. So that's a reduction that could occur. The other thing that's in my cell is liquid mercury. So that would have to oxidize to make a reaction occur. So let's look for mercury here. Here we see the reduction of mercury 2+ to liquid mercury. So the oxidation would be just the opposite of that. So we had a reduction potential of 0.854 positive volts. So we'll make an oxidation potential of negative 0.854. So based on what we've just seen there, a potential reduction is MnO2 plus 4H plus 2 electrons makes Mn2 plus 2H2O. That's a potential reduction. And we saw that the standard reduction potential for that was a positive 1.23 volts. The oxidation that would have to happen in this situation would be liquid mercury oxidizing to Mercury 2+, and that would give up 2 electrons. The oxidation potential for this would be the opposite of the reduction potential that we saw for Hg2+ reducing to Hg. That reduction potential was a positive 0.85, so we're going to make this a negative 0.85 volts. When I find my cell potential by summing these two together, I will get a cell potential of a positive 0.38 volts. So because E cell is positive, this reaction is spontaneous. The number of electrons gained and lost are the same, so I can just sum these up to get my overall reaction. MnO2 plus 4H plus Mercury makes Mercury 2 plus Mn2 plus 2 waters. This next quiz-can question is asking me to write the equation for the reaction that occurs, if there is one, when aluminum metal is added to a solution that has potassium ions in it. Stop the video, see if you can predict this one. It should be easier than the last one, and I'll give you an answer. Well, the problem was telling us that there was solid aluminum and potassium ions. So the aluminum would have to oxidize here to make Al3+. That's the standard way that aluminum would oxidize, and that would give us up 3 electrons. Potassium would have to reduce by gaining an electron to become just metallic potassium. Now, would this reaction actually occur? Well, we're going to have to find out what is the standard oxidation potential for the aluminum oxidizing, and we're going to have to figure out what is the standard reduction potential for the potassium reducing. Let's go back to our chart of standard reduction potentials. Here I can see the reduction of aluminum 3 ions to aluminum, and that reduction is a negative 1.66 volts. So as an oxidation, I would reverse that reaction and get a positive 1.66 volts. Now let's look for potassium. There it is. The reduction of potassium ions to metallic potassium has a reduction potential of negative 2.93 volts. Now, knowing that, let's put those together and find our E cell. So our oxidation potential was a positive 1.66 volts. Our reduction potential was a negative 2.93 volts. So our cell potential is the sum of these two, and that's going to come out to be a negative 1.27 volts. Now, since E cell is negative, we do not have a spontaneous reaction here, and so we can't write an equation. This is a no reaction situation. Before we move into this next section, I want to stop for a little bit and show you a little demonstration of a very simple voltaic cell being set up. As you watch this, I want you to see how simple it is to make this cell, and I'd also like you to take note of what the voltage reading is on the voltmeter that's hooked up to this cell. Well, I have a few items here that I'm going to use to assemble a voltaic cell. The first thing I'm going to do is I'm going to create a half cell that's a copper 2 half cell. So into this beaker, I will pour some aqueous copper 2 sulfate solution. You can see its characteristic blue color. That's the color that copper sulfate looks. And then I have a spool of copper wire. So this will be my electrode. Snip my piece of copper wire and I'll put that into the copper 2 solution. The other half cell is going to be a zinc sulfate solution. So here I have a solution of zinc sulfate. And I'll pour some of that into another beaker. And I have a sheet of metallic zinc here. So I'll cut a strip of zinc off of that. and I'll set my piece of zinc in the zinc solution. So now I've got a copper 2 half cell and a zinc 2 half cell. The next thing I want to do is hook them up in an electrical circuit. So I'm going to take this alligator clip it onto my piece of zinc, and I'm going to take another lead and hook it up to my piece of copper wire. And I have a voltmeter here, so I can measure the potential that's generated. So from one lead of the voltmeter, I will clip up the jumper wire that's going to the piece of zinc, and to the other lead, I'll hook up the jumper wire that's attached to the copper wire. And if I look at my voltmeter, you can clearly see that it's reading 0. There's no potential generated at all. But if you look at my voltaic cell, you can see the reason why. There's no way for the current to make the circuit because I'm missing a salt bridge. Well, I have here a piece of string that's been soaking in a potassium iodide solution for a while, and I'm going to see if I can use that as a salt bridge. So this is something that's going to allow the solution to leak ions into and out of the solution on both ends. Now I put it in the zinc sulfate end, and you can see that the voltmeter is still reading 0. Look what happens to the voltmeter when I dip it into the copper 2 half cell. I suddenly have a voltage reading of it's negative 0.82 volts. So that just means I have my leads switched around, but that's not too far off from the standard cell potential. Notice, however, that it's changing. As the reaction proceeds, the voltage will slightly change. Watch what happens when I reverse my two leads. Now my voltage reads positive because I've got the electrons flowing through the voltmeter in the correct direction. Simple voltaic cell. Now we're going to start to make some links between electrochemistry and some other branches of chemistry that we've explored throughout this course. So for example, thermodynamics. The idea of work came up when we were studying thermodynamics, and in a mechanical system we have seen that work is equal to force times the change in distance. And when that's pressure volume work, we've seen that as work as pressure times delta V. It's a negative value. In an electrical system, there's an analog to pressure and change in volume and force and change in distance, and that is that the charge times the potential is equal to the work. Now, if you think about the charge, that can be calculated in an electrochemical cell by taking the number of moles times Faraday's constant. Remember, Faraday's constant tells you how many coulombs per mole of electrons. If you multiplied 96,500 coulombs per mole times the number of moles, you'd have the total charge. And then if you multiplied that by potential, which in an electrochemical system is E cell, you would have work in terms of electrochemistry. So for an electrochemical cell, the maximum work that's available is equal to the number of moles of electrons transferred in the redox reaction times Faraday's constant times the cell potential. But we also know that max work from thermodynamics is equal to the opposite of delta G, negative delta G. So that means delta G is equal to minus N times Faraday's constant times E cell. By equating what we know about maximum work from thermodynamics to what we know about maximum work from electrochemistry. Now let's link this to equilibrium. We know from our studies of thermodynamics and equilibrium that delta G naught is equal to minus RT times natural log of K. But we also now know that delta G is equal to minus N times Faraday's constant times E cell. And if it's delta G naught, then it's E cell naught. So we can set these equal to each other and then solve for E cell. So E cell is equal to minus R times T times the natural log of K divided by N times Faraday's constant. Now if we actually put the numbers in here, for R we would have 8.314 joules per mole per Kelvin times temperature, well this is standard conditions, so 298 kelvins, divided by number of moles, that's just going to be N, times Faraday's constant. Faraday's constant was 96,500 coulombs per mole of electrons. Now, if you crunch the units down here, moles are going to drop out, kelvins are going to drop out, and you get joules per coulomb. But a joule per coulomb is a volt, so our units simplify to just volts. This is multiplied by natural log of K. So E naught cell, in its simple form, is 0.0257 volts divided by the number of moles of electrons transferred in the redox reaction times the natural log of K. Now for traditional units, this is often expressed in base 10 terms. And I'll leave it to you to figure out the math behind this, but you can convert that and you will end up with this expression. E cell naught is equal to 0.0592 volts over N times the base 10 log of K. So both of these are legitimate expressions for E naught cell, but this is the one that's used traditionally in base 10 log units. So let's answer this question. For a copper 2, silver 1 silver cell, the standard cell potential is 0.46 volts. And the question is find Kc for this reaction. So what is our link? It's the equation that we just had that defines E cell in terms of K. So we know that the standard cell potential is equal to 0.0592 volts divided by N, number of moles of electrons transferred, times the base 10 logarithm of K. And K is what we're trying to solve for here. So if we take number of moles times the cell potential and divide by 0.0592 volts, we'll get the log of K. So that means K would be equal to 10 to the number of moles of electrons transferred times standard cell potential divided by 0.0592 volts. So how many electrons are transferred? Well, the actual reaction that would take place in this cell is not the one that we're looking at, because silver would really reduce. It's got a higher reduction potential. So Ag would gain an electron, Ag plus would gain an electron to make Ag, and Cu would oxidize to Cu2 plus and release 2 electrons. So we'd have to multiply this top reaction by 2, and that would mean that 2 electrons were lost and 2 electrons were gained. So N is 2 here. So let's plug that in here. 10 to the 2 times, and it said that E cell was a positive 0.46 volts, and then we're dividing by 0.0592 volts. Multiply that all out and raise 10 to it, and you end up with 3.5 times 10 to the 15th. However, since this reaction that we were doing this for is the reverse of the one we're trying to find the potential for, the actual K for our reaction is 1 over 3.5 times 10 to the 15th, which equals 2.9 times 10 to the negative 16th. Remember the demonstration that we saw where we had the copper and zinc voltaic cell in action? The voltmeter showed a potential for that cell of about 1.00 volts. The standard cell potential for that cell is actually 1.10 volts if you work it out theoretically. So why was our reading lower than the standard cell potential? Well, it has to do with the fact that we didn't have the same concentration in the cell as the 1 molar concentrations that would be expected for the standard cell potential. And another reason might be that the temperature wasn't 25 degrees C, which would have to be for standard conditions. So another thing that we can explore is what is the relationship between the actual cell potential and the temperature and the equilibrium position of a reaction that can be changing. Well, let's start out looking at this from the standpoint of thermodynamics. We know that delta G is delta G naught plus R times T times the natural log of Q. But we also know that delta G is equal to negative N times Faraday's constant times E cell. And we know that delta G naught is negative N times Faraday's constant times E naught cell. So substituting, we would find this minus N times Faraday's constant times E cell equals negative N times Faraday's constant times E naught cell plus R times T times natural log of Q. If we divide both sides of the equation by negative N times Faraday's constant, we come up with this equation. The cell potential, E cell, is equal to the standard cell potential minus R times T over N times Faraday's constant, and that's also negative, times natural log of Q. Now when you take the negatives out of here and replace the R and T and Faraday's constant by real numbers, you get this equation. E cell is equal to E naught cell minus 0.0257 volts over N times the natural log of Q. Or in the base 10 terms that are much more familiar here, like we said earlier in electrochemistry, we could rewrite this E cell is E naught cell minus 0.0592 volts over N times the base 10 logarithm of Q. This equation allows us to predict what the cell potential is going to be under changing values of Q. For example, we're asked here to find the cell potential at 25 degrees C of a zinc-2, copper-2 copper cell, where the copper ion concentration is 0.01 molar and the zinc concentration is 1.0 molar. Well, first of all, let's establish what the reaction is here. Zinc is the thing with the highest oxidation potential, the lowest reduction potential, so it's going to oxidize to zinc 2 plus and give 2 electrons. Copper is least active, and so it's going to reduce from copper 2 to copper. E naught oxidation for the zinc oxidation is going to be a positive 0.76 volt, if you look that up. For the copper reducing, the standard reduction potential is going to be a positive 0.34 volt. That was one of the examples that we worked with in the last video. So the cell potential, the standard cell potential for this reaction is positive 1.10 volts. When we add these together, we get zinc plus copper 2 makes zinc 2 plus copper. N, the number of electrons transferred, is going to be 2. And Q will be defined by the concentration of zinc ions divided by the concentration of copper 2 ion. So using the Nernst equation, E cell equals E naught cell minus 0.0592 volts divided by N times the natural log of Q, we should be able to predict what the actual cell potential will be here. First of all, let's evaluate what Q is. Concentration of zinc ions, they told us, is 1 molar. Concentration of copper ions in the solution, they have told us, is 0.010 molar. So Q is going to be equal to 100. So our cell potential under these conditions is going to be equal to the standard cell potential, which we have determined is positive 1.10 volts, minus 0.0592 volts over N, which is 2, times the natural log of 100. So that means E cell under these conditions with these concentrations is equal to positive 1.04 volts. So this represents a battery that is going dead, essentially. Under standard conditions, 1.10 volts are possible, but when the conditions change to what they are now, we have 1.04 volts, less potential. Here's another possible way that this could be looked at. A voltaic cell is constructed by making a nickel electrode in a nickel 2 solution, and then connecting that to a chromium electrode that's dipped into a solution whose concentration you don't know, but it contains Cr3+. The potential, the actual reading on the voltmeter, is 0.552 volts, and we're going to use the information that we have here to calculate what is the chromium ion concentration in the unknown solution. Let's start out by drawing a picture of this cell. In one half cell we have nickel ions, nickel 2, and we have an electrode that's made of nickel. In the other half cell, we've got a piece of chromium, and we have a solution of chromium 3+ ions, but we don't know the concentration. We do know the concentration of the nickel solution, and it's 1.20 molar. And of course there would have to be a salt bridge connecting these so that the circuit was complete, and there would be a wire connecting the two electrodes. That wire is hooked up to a voltmeter, and it tells us that 0.552 volts is the reading. Well, let's determine which direction the electrons are flowing in and what the actual reaction for this cell is. We have two potential reductions. Either nickel 2 could reduce to nickel, and the reduction potential for that, if you look it up, is negative 0.28 volts. Or we could have chromium 3+ reducing to chromium, and the reduction potential for that half reaction is negative 0.74 volts. So clearly the one that has the most positive value of reduction potential is the nickel reduction. So that's our actual reduction. So in our cell, nickel 2s are reducing to nickel, and as we've seen, our reduction potential is equal to negative 0.28 volts. But chromium is oxidizing to chromium 3s and giving up 3 electrons, and the oxidation potential is the opposite of the reduction potential for the reverse reaction. So we'll have positive 0.74 volts. We sum this together, we see that the cell potential, the standard cell potential, is equal to a positive 0.46 volts. Now when we add the reactions together, to make the electrons gained and lost the same, we're going to have to multiply the top reaction by 3 and the bottom reaction by 2. And when we do that, we'll have 6 electrons transferred. So that means N, when we go to apply the Nernst equation, would be 6. The overall reaction is 3 nickel 2+ plus 2 chromium makes 2 chromium 3+ plus 3 solid nickels. Q for this reaction is going to be equal to concentration of chromium 3 squared divided by concentration of nickel ions, nickel 2, cubed. Now since our objective is to determine what is the concentration of the chromium 3 ions, since we know the concentration of the nickel 2 is 1.20 molar, if we can calculate Q, we should be able to do it. Now the Nernst equation would allow us to calculate Q. Let's plug in the values that we need. Let's rewrite the Nernst equation here. E cell, the actual cell potential, is equal to the standard cell potential minus 0.0592 volts divided by N times the base 10 logarithm of Q. So it's Q we're trying to solve for. Well, if we subtract the standard cell potential from both sides, we'd find that E cell minus E naught cell is equal to negative 0.0592 volts over N times the base 10 logarithm of Q. So multiplying both sides by N and then dividing both sides by 0.0592, we get this. E cell minus E naught cell over 0.0592 volts times N is equal to the base 10 log of Q. So that means Q is equal to 10 to the N times E cell minus E naught cell over 0.0592 volts. So let's put some numbers in there. 10 to the 6 times our actual cell potential was 0.552 volts minus the standard cell potential, which is 0.46 volts, divided by 0.0592 volts. Now, when you work this all out, Q turns out to be equal to 4.74 times 10 to the negative 10. So now let's use that to find our unknown. Knowing that Q is equal to 4.74 times 10 to the negative 10th, and that that's equal to concentration of chromium 3 plus squared over concentration of nickel 2 cubed, we can solve for concentration of chromium 3. So concentration of chromium 3 is equal to the square root of 4.74 times 10 to the negative 10th times concentration of nickel 2 ions cubed. Just solving that equation for chromium 3 concentration. So to get our final answer, chromium 3 plus is equal to the square root of 4.74 times 10 to the negative 10th times 1.20 moles per liter cubed. So therefore, our chromium 3 plus concentration is equal to 2.61 times 10 to the negative 5th. You can see the value of doing this. If it were necessary to quickly measure the concentration of some ion in solution, you could develop a sort of ready-made voltaic cell that only needs a salt bridge and the electrode to be dipped into the solution, and the voltmeter gives you the information that you need to calculate chromium 3 concentration. Since most voltmeters are now electronic, you could just simply program the voltmeter to read not volts, but concentration of chromium ions. And in fact, that's been done. Lots of kinds of probes have been developed that all you have to do is dip the probe into the solution in the electronics, set up this voltaic cell, read the voltage, convert it all, and tell you what's the concentration of the unknown. A pH meter would be a good example of this. Now let's just take a little time at the end here to talk about some practical applications of voltaic cells. A car battery is a good example of a voltaic cell. In the car battery, you have a lead grid, and then that alternates with another lead grid. And every other lead grid here is connected to a different electrode. So half of them are connected to the negative terminal of the battery, half of them are connected to the positive terminal of the battery. The anode is filled with lead, and the anode reaction is that lead, that Pb, solid spongy lead that's in the grid, reacts with sulfate ions, SO42-, that's in the battery acid, which is H2SO4, and produces solid PbSO4, lead sulfate, and that's an oxidation, so 2 electrons are released. The other grids, the cathode grids, have PbO2 in them. And this PbO2 reacts also with sulfate ions, SO42-, and requires H pluses from the H2SO4 to produce same product, PbSO4, and 2 waters. One of the things that makes this really nice is that this electrolytic solution for both halves of the reaction is the same solution. It's H2SO4. And so you don't need a salt bridge. You can just put the electrodes in the same solution, and that's how a car battery works. This voltaic cell actually produces about 3 volts. So your car, which typically operates on a 12-volt system, has a gang of 4 of these things hooked together in series to amplify the voltage. Another common battery, sometimes called the zinc carbon dry cell, the original flashlight battery. If you cut one apart, what you find in the middle is a cathode, which is just a graphite rod. It's not part of the reaction. It just carries electrical current. The anode is a piece of zinc. So if you peel off the mylar or plastic outside, you'll find a can that's made of zinc, and that's actually the anode. And then in between is a paste, and that paste has manganese dioxide and ammonium chloride in it, and then ground up bits of carbon are scattered throughout this paste to make it easier for the electrical current to reach the reactants. So what's happening at the anode is zinc is oxidizing to make zinc 2+ and 2 electrons. So the case that holds the battery together is gradually being eroded. The zinc is getting thinner and thinner. Of course, battery designers have to think about that and make sure that it's thick enough that by the time the battery is dead, by the time the battery runs out, the zinc doesn't wear through. So zinc can't be the limiting reactant here. The cathode reaction, the MnO2 that's in that paste is going to react with ammonium ions that are in the paste, collect the electrons from the oxidation, and reduce to Mn2O3, manganese 6 oxide. And it'll produce ammonia, which dissolves in water pretty readily, so it stays in that paste, and then some more water that just makes the paste more moist. So 2 electrons are transferred. They go from the anode, which is the zinc case, to the cathode through the electrical circuit. So the button at the top is collecting the electrons, and the case on the bottom is releasing the electrons, and they're traveling around and around in the circuit, and then you hook it into your flashlight or whatever, and you make the thing operate. Now there's an alkaline version of this that's much more common nowadays than the version that I've just gone through. So the alkaline dry cell operates this way. The zinc actually reacts with hydroxide ion and produces zinc oxide and water, still releases 2 electrons. Cathode reaction is very similar to the one in the acid dry cell, except water is on the left-hand side, not the right, and you still make Mn2O3, but now you make 2OH-. So it's called a alkaline dry cell because it produces a basic environment as the reaction goes on. Then there are other types of dry cells that use different kinds of reactions. A mercury cell battery is one example of the little button batteries that are used to power watches or hearing aids or things like that. And the anode is usually zinc, so you still have this zinc alkaline reaction, zinc plus 2OH- that you would have in a flashlight battery. But here the cathode is some mercury oxide plus water collecting the electrons to produce liquid mercury and 2 hydroxide ions. Now obviously liquid mercury is a problem. That's a really toxic substance that we wouldn't like to have people be exposed to a lot, and we don't want it in our environment. And so these mercury cell batteries have an issue. And so they've been largely replaced with something that uses silver rather than mercury, but has a very similar reaction. The advantage, they hold their voltage really well right up until they're nearly dead. And so instead of seeing a gradually decaying voltage, you'll see it stay at about the same potential until just about the moment that it's dead. Another thing that would probably be much more a part of your future than my past is a hydrogen fuel cell or other kinds of fuel cells. I'm using hydrogen as a good example here. This isn't exactly a battery. It's not exactly the same thing, but it is a voltaic cell. The anode half reaction occurs when hydrogen is pumped into this container and it oxidizes, collects some OH- to make H2O, and that gives up 2 electrons. These carbon electrodes that the hydrogen gas is flowing through into the middle actually do this oxidation on the way in to the center of the fuel cell. Electrons are produced, pumped over to the other electrode, and then reduction can occur. And oxygen that's coming in from the other side and passing through this electrode, that oxygen reacts with two waters, collects 4 electrons, so this isn't balanced, and produces hydroxide ions. So in the middle, we have a KOH solution and H2O that's being used by the oxygen in reduction and produced by the hydrogen in oxidation. So if you sum this up, you'd have to multiply the top half reaction by 2, and here's what you end up with. 2H2 plus 4OH minus plus O2 plus 2H2O yields 4H2O plus 4OH minus. What's the net reaction? You can take the OH minuses out, and 2 of the H2Os can be taken out, and the net reaction is 2H2 plus O2 makes 2H2O. What's your waste product? Water, perfectly safe. What are your inputs? Oxygen, which there's plenty of, hydrogen, which there's a lot of, but it's harder to get in its pure form. But it's a totally clean reaction, and it's extremely efficient, much more efficient than conventional batteries. And it's much more efficient also than conventional combustion reactions. And so you're going to probably see in your lifetime different kinds of fuel cells, perhaps even this hydrogen fuel cell being used to generate power. One of the disadvantages right now is to make them practical, they have to be made huge. They have to be very, very large, and it's expensive. And that technology could change over the course of time, and you might find fuel cells becoming more and more important part of our economy and how you power your life.